Greetings, class! Did you know that the estimated energy required to form our entire universe is a staggering 10 to the power of 70 joules? While a single, ordinary human heartbeat exerts just 1 tiny joule, it's honestly an unimaginable scale. But here is the wild part. The exact same fundamental laws of physics govern both of those phenomena. Today, we will study energy, efficiency, and power. Let's jump right in by pinning down our core concept. What actually is energy? Fundamentally, it's the stored ability to do work. Think about winding up a little mechanical toy spring. By physically applying a force over a distance, you are doing work, and you're storing energy right there in that spring. And the golden rule is without energy, an object simply cannot do work. Period.
Here are the core details regarding this topic. Review them intently for they are deemed crucial for your finals.
Following up on that absolute rule of physics, no energy literally means no work. But the moment you let go of that wound-up spring we just talked about, it exerts a restoring force over a distance to move the toy, so it does work. Now, it's totally crucial to remember that both energy and work are scalar quantities. That means they only have a magnitude, no direction. And beautifully enough, they both share the exact same unit of measurement, the joule. Now, when we look at typical energy values, it traces this absolutely fascinating path of magnitude. We can start super small at the microscopic level. We're talking 10 to the minus 13 joules for the radioactive decay of a nucleus. Then, moving up through the energy of speech hitting your ear or moonlight on your face, we finally reach the steady 1 joule beat of a human heart. And scaling up a bit more, we get 1,000 joules released just by burning a single match. Okay, scaling up even further, things get pretty incredible. Amusingly enough, a single large cream cake contains a massive 1 million joules. I mean, you'd need some serious, heavy manual labor to work all that off. And the scale just keeps going. From a tectonic earthquake to the mind-blowing rotational energy of our Milky Way, all the way to the formation of the universe itself, the joule remains the universal currency of physics. Now for your syllabus, you really need to be able to precisely classify energy into different forms. We've got mechanical states, which include gravitational potential energy. That's dictated by an object's mass and its position in a gravitational field, and kinetic energy, which is all about motion. We also have elastic potential, just like our spring example, and then we expand outward into electrical potential and the vast, swirling spectrum of electromagnetic radiation, which of course includes solar energy from the sun. Wrapping up our energy forms with internal, chemical, and thermal states, we can actually elegantly map out how energy converts in a simple closed circuit. Let's take a standard battery connected to a lamp. First off, the stored chemical energy in the battery converts into electrical energy, which travels right through the wires. Then it transforms into the light energy we actually want, alongside some internal thermal heat that just warms up the bulb. So, here's a concept you absolutely must grasp because it's a huge real-world issue. What the media constantly calls a global energy crisis is, scientifically speaking, actually a fuel crisis. Why is that? Well, whenever we drive a car, the engine converts highly useful finite chemical petrol into kinetic energy, but vast amounts of it are just wasted. The end result is that concentrated useful chemical energy irreversibly dissipates into the atmosphere as entirely useless thermal heat. But despite this massive fuel crisis, the grand total of energy in the universe remains absolute and constant. This is the ironclad law of conservation of energy. Energy simply cannot be created, and it cannot be destroyed. It can only be converted from one form to another. And guys, this is exactly why a perpetual motion machine is a strict physical impossibility. You literally cannot cheat the universe.
Listed are the main insights for the heading discussed. Note them specifically since they are highly relevant for exams.
Now, because friction guarantees that some energy is always going to be lost to the environment as thermal heat, we desperately need a way to measure a machine's actual effectiveness. So we calculate efficiency. It's a strict ratio, the useful energy output divided by the total energy input. And since you're always losing a little bit to heat, when you express this as a percentage, it can absolutely never exceed 100%. Let's meticulously apply this idea with worked example 5C. Imagine a man using a pulley system to lift a 480 Newton load vertically up 3.5 meters. First, we look at his physical input. He pulls with 200 newtons of force over 10.5 meters of rope. That totals 2,100 joules of work put in. But the useful output, the actual load being lifted, only comes to 1,680 joules. So if we divide that useful output by the total input, we achieve a highly respectable efficiency of exactly 80%. Okay, but having energy isn't the whole story. Power dictates the actual rate at which work is done. Power simply equals the work done divided by the time taken, and we measure this in watts, which is exactly 1 joule per second. This perfectly explains why a Formula One racing car easily outpaces a standard family sedan. Even if they're doing the identical amount of work to move down the track, the racing engine converts that energy vastly faster. And just like energy, power outputs range wildly. A tiny 1-watt bulb converts 1 joule every single second. A small calculator quietly operates on 10 to the minus 6 watts. Moving up the scale, a standard loudspeaker outputs 10 watts. A manual laborer averages a steady 100 watts. And a heavily working water buffalo outputs an impressive 1,000 joules every second. Scaling way up to massive electricity generating stations running at 10 to the 9 watts, we need to pause for a really critical physics technicality. In everyday life, we might call a really strong person powerful. But in physics, mere force does not equal power. You could be sweating intensely, pushing with all your might against a giant stationary rock. But if that rock doesn't move, your distance is zero. Zero distance means zero work done, which means, technically, you are producing exactly zero power. Now, pay close attention to this next part because we are going to derive a highly useful equation for your exams. Consider a force, F, moving a distance, x, at a constant velocity, v, over a specific time, t. Step 1, we know work equals force times distance. Step 2, since power is work over time, we divide both sides by t. Step 3, distance over time is the exact definition of velocity, therefore we elegantly derive this. Power equals force multiplied by velocity, or P equals FV. Definitely commit this one to memory. Let's immediately apply that new formula in worked example 5D. An electric motor lifts a 1.5 Newton weight 120 centimeters in 2.7 seconds. Now watch out, here is a classic exam trap. You absolutely must convert that displacement into standard SI units. So 120 centimeters deliberately becomes 1.2 meters. The work done is 1.5 times 1.2, giving us 1.8 joules. Divide that by 2.7 seconds and our power output is a clean 0.67 watts. All right, let's firmly summarize today's explainer. Energy is the scalar ability to do work, measured in joules. The law of conservation strictly dictates that energy is never actually lost, it only changes form. The so-called fuel crisis is simply the irreversible conversion of highly useful chemical energy into totally useless thermal heat. Efficiency tracks our useful output, and finally, power is the scalar rate of doing that work, measured in watts. I'm going to leave you with this final provocative thought to ponder deeply as you review your notes. If the absolute law of thermodynamics firmly dictates that the universe's total energy is permanently constant and that energy can truly never be destroyed under any circumstance, what exactly is humanity actually losing during a global fuel crisis? Think carefully about the quality and the concentrated usefulness of that energy right before it dissipates. Thank you so much for joining me for this explainer. Study hard and keep seeking those precise answers.
Important terminology for this topic is shown on the screen, arranged according to various exam boards. These terms demand focused attention during revision as they are highly significant and must never be overlooked. Furthermore, a past paper evaluation is included for each board and paper format. Give this paper attention too, since it will strongly enhance and refine your preparation. Additionally, aims to grasp the meaning and usage of every term instead of rote learning them individually. Consistent practice of these terms in past paper questions will greatly boost your precision and overall exam results.
Please subscribe our channel to get more educational videos. Thank you.